Hi, welcome to the third interrogation video. Let's just get right started. We are now ready to begin analyzing circuits. To analyze a circuit means to find 1. The potential difference across each circuit component, 2. The current in each circuit component. So we learned that the potential difference and current are the most important thing in a circuit. So because charge is conserved, the total current into the junction of figure 20.4 must equal to the total current leaving the junction. That is, the sum of the current going in equals the sum of the current going out. So we know that current is, the unit of current is coulomb per second, meaning that it's measuring the amount of charge flowing through a certain point in a certain time interval. So so let me quickly draw a diagram. So yeah, these two resistors are connected in parallel. So at this point, for example, the current going in equals the current going out at this point. So, and when we think about it, current is measuring how many the amount of charge. So it's measuring how, like, the amount of electrons flowing through that point at a certain time. So, and then when the electrons get separated into two paths, like the current going into two paths, the energy is used up by the resistors, like a light bulb or something, and then the electrons get recombined into this one path. So since electrons don't go anywhere, we know that the current has to be the same at these 2 points. This statement, which you met in chapter 27, is Kirchhoff's junction law. Yeah. Because energy is conserved, a charge that moves around a closed path has a potential difference equal to 0. We apply this idea to the circuit of figure 28.5 by adding all of the potential differences around the loop formed by the circuit. Doing so gives delta V loop equals sum of all potential differences, which equals 0, where delta Vi is the potential difference of the ith component in the loop. So so the first part, delta V loop, saying that in a complete circuit, so with, like, for example, it's saying that when you add up all the different components in the circuit, like their potential differences, it should equal to 0. So for example, if this is 6 volts, these two has to equal, when you add up these two resistors, they have to equal to 6 as well in order to or they have to be -6 to have a total sum of 0. Kirchhoff's loop law can be true only if at least one of the component is negative. To apply the loop law, we need to explicitly identify which potential differences are positive and which are negative. Yeah, just like I said. So it has the first sentence is saying that there has to be a power supply or battery with a positive. Wait. No, never mind. It's saying the first sentence saying that there has to be at least one resistor that's negative in order to balance the positive potential difference of the battery or the power source. So we need to know which part are positive and which part are negative. So in this case, so for example, this is the battery 6 volt. These two has to be -3 volts. For example, it can be other values, but these two have to add up to -6. So when you add these up, they equal to 0. What is the magnitude of the potential difference across each resistor in this figure? So so we can tell that these two resistors are connected in parallel, and then this is the battery. So So we're trying to find what V1 and V2 are. So according to Ohm's law, all the potential differences when added up should be 0. So 50 plus V1 plus V2 equals 0. And also we need Ohm's law in this case we can integrate Ohm's law into this Kirchhoff's law. So Ohm's law is V equals IR. So potential difference equals current times resistance. So when we manipulate this equation, so we know that V1 and V2 are probably negative since they're resistors. They have that negative potential difference since the battery has positive potential difference. So since these two are negative, when you move over, it's like this. And then when you substitute Ohm's law into this, it becomes IR1 plus IR2. And we know that when in a series circuit, the current and everywhere are the same. So so we can pull out I since it's the same for both resistors, R1 plus R2. And we know and R1 R2 are given to us, so 40 plus 60 equals 100. So when you divide that over, it becomes 0.5 amp equals the current. So, and then we need to use that current to find out the potential difference. So again, V1 equals IR, so 0.5 times 40 ohms equals 20 volts. And then V2 equals 0.5 amp times 60 ohm, which is 30 volts. And then when we check to make sure it works, it's 50 volts minus 20 minus 30 is 0. And we know that, and that's correct. Thank you for watching.